That's GeoGebra. Oops, I'm supposed to share the screen and go back to this. Oops. So there's our differential equation that we just looked at. You can't actually solve that. So how do you go about finding values for y of t if you don't actually know the formula? So functions is a rule for assigning y value to each t value in the domain. So initial value problem like this tells us the t and y coordinates for the initial condition. That's here. If you can't get a formula for y of t, how can you estimate other values? And that's what Euler's method does. So keep in mind that slope is change in y over change of t, right? You remember that from algebra at some point. And that the derivative is the slope of the tangent line. So an equation like this is saying if you know the point that you're at, your t value and your y value, you know what the slope of the tangent line is to the curve that goes through that point. To a solution curve has to have this as its slope of the tangent line. So if we want y of 3 for this equation, and we did it with GeoGebra and we ended up with this as our y of 3, the question is what's Euler's method? So we can calculate this by hand, and so we'll do an example by hand just to sort of give a feel for this, and we'll look at how we can actually automate this a little bit. So we're starting with our initial condition is 0 minus 3. So we're starting at 0 and minus 3. We'll take delta t to be 1. It's not going to be particularly accurate, but it'll at least get us started. Delta t equals 1. So what's our slope? Slope, again, is the slope of the tangent line. It's dy dt at the point that we are interested in. So dy dt is 1/3 y times t squared. So 1/3 times y, which is minus 3, plus t squared. T is 0, so 0 squared, that equals minus 1. So what's delta y? Well, remember from this, delta y equals m delta t. So delta y is going to be slope times delta t, that's minus 1. So what's our new t? We've gone 1 unit to the right, so 0 plus 1 is 1. And we went 1 unit down, so minus 3 plus minus 1 is minus 4. Great. So we bring these over. Those are where we're now at. So we go to 1 minus 4. Great. We just continue with that. So this becomes 1. Slope is now 1/3 times minus 4 plus 1 squared. This is minus 4/3 plus 1, so it's minus 1/3. Delta y is delta t times slope. So 1 times minus 1/3 minus 1/3. So what's our new t? 1 plus delta t, that's 2. What's our new y? Minus 4 minus 1/3 is minus 4 minus 1/3, which is minus 13/3. Then these, we just plug them back in here. This becomes our old t and our old y, and we want to calculate the new t and the new y. Keep delta t at 1, the slope becomes 1/3 times minus 13/3 plus 2 squared, plugging in the old t and the old y into our formula for the slope. And that becomes minus 13/9, and 2 squared is 4, which is 36/9. That's 23/9 is our slope. So delta y is 23/9 times delta t. Our new t is 2 plus 1, which is 3. And our new y is minus 13/3, which is minus 39/9, plus 23/9, which equals minus 16/9. Yep. So that's not a good estimate, right? Our estimate is minus 16 over 9, and y of 3 is actually 3.63. So what happened there? So let's go back to GeoGebra. Pause the recording for a moment. So here we are back at GeoGebra, at least I hope we are. It's sometimes hard to tell what screen you're actually on. Here's our curve that starts through, it's a solution to this equation. It goes through the point A being 0 minus 3, and B then is the actual point that we're trying to estimate using Euler's method. So what were the points we got? We started with A being 0 minus 3, and then in Euler's method, the next point we got was 1 comma minus 4. So how did we get that point? What was that calculation that we did? Well, the slope at point A is minus 1. And if we're going to go 1 unit to the right along a line of slope minus 1, we go from A to C. So we'll go back to our tools and we'll pick up segments. So there's our first step. Then the second step, we got to C, we calculated the slope there, and we went along the line of the slope at C. And that actually took us to the point 2 comma minus 13.3. So we went 1 unit to the right, and then we know what the slope is, so then we calculated the delta y. So the slope at point C brought us to D. And then we're going to go 1 more to the right, given that what the slope is D. So we calculate the slope at D. If we go 1 unit to the right and then up the line with the correct slope, we'll end up here somewhere. And so the last point that we actually used was 3 minus 16/9. And that's that point. And we can connect those. So there's Euler's method. The problem with Euler's method is if your step size is too, well, in general with Euler's method is that these quick curves in the solution curve, right? So you start at point A and follow the solution curve, there's a minimum, and then it snaps upward pretty quickly. And Euler's method can't really catch that. It didn't really notice that the signs of the slopes had changed until it got to point D, and then it was like, oh, got to catch up. So it went to E, and then it would be steeper and steeper, but there's still a big gap, right? The gap from B to E, right? That's your error, and that's a pretty serious thing. We'll talk a little bit about how error shows up in Euler's method. I haven't found a good way to do iteration and stuff on GeoGebra, but we can actually do this on Microsoft Excel. So we're going to move to that real quick here. Okay, so here we are with Excel. We want to approximate our solution to our differential equation, right? So we'll just put this up here at the top. What are we trying to do? We want to approximate the solution to dy dt equals 1/3 y, plus t squared, with the initial condition y of 0 equals minus 3. We want to know what, when t equals 3, what's the y value that you actually have. So that's what we want to do. And so that we can actually see that, we will do merge and center as just sort of a title thing there. Okay, so how do we go about doing this? We'll just set up the same table. Old t, old y, delta t, slope, delta y, new t, new t, new y. Just typed everything in. You can move around with the arrow keys, so that's what that is. I'm just using the arrow keys to move around. So we started at 0 minus 3. Delta t we're going to take to be 1. Slope is equal to, so whenever you want to calculate something, you have to tell Excel that you're going to calculate it, so you have to use an equal sign. Once you have the equal sign, it knows you're trying to do something, you can enter things. So we want 1/3. Oops. Excel really likes parentheses. So 1/3 times, and now I'm just going to use the left arrow key to go over to the y, because it's 1/3 y, and then plus, I'm going to use the left arrow key again to go over to the 0 squared, right? So when you put in the plus, it knows that you're done with that before, and it says, okay, now you can go on and enter another cell. So that's 1/3 y plus t squared, and it's minus 1. Delta y equals, I want to do a calculation, that's slope times delta t. So d4 times c4. And note, column D is this, row 4 is that, so this is cell D4. So my new t is equal to my old t plus my change in t, delta t, and my new y is equal to my old y plus my change in y. Great. And I want to carry those over, so let's say old t is equal to new t, and that was just a 1 left click there, and I want old y equal to new y. And then I want to repeat the same calculations I did, but with instead of 0 and minus 3, I want to do with 1 and minus 4. So we'll take this, and if you go shift and then right arrow, you can select those. Shift again and down arrow does that. And then control R is the, oh, I hate it when it does that. Control R is the command that tells you to do the same calculations going down. Control D, not control R, control down. So there's our solution, right? 2 minus 4.33. And then we can actually, now that we've actually done the self-reference, right, saying that old t is equal to this, we can actually ask it to just, you know, do the next 2 steps. So there's our points. And you can actually graph these, right? Highlight that, go to insert where it says charts, recommended charts. It'll give you lots of charts. It's starting off with that, but really that would look better, right? That's a little bit more of the curve that we're looking for. And this is another one, same kind of a line graph. This is a scatter graph. So if we do a nice line graph, well, we'll do this one, the scatter graph. So when y is 0, t is minus 3. When t is 0, y is minus 3. When t is 1, y is minus 4. When t is 2, y is 2. When t is 3, y is minus 1.778. So that gives us our graph. This is the same graph that we had in with GeoGebra. So one nice thing about doing it on Excel is you can change things, right? So if I change this to a 0.1, if I change my step size from 1 to 0.1, I get a little bit of a change, right? And change that. And so we want actually all the step sizes to be 0.1. So highlight those cells and we'll go Control D, so the step size is 0.1. And it looks like this, which is almost a straight line, right? Notice that your slopes are all pretty much close to -1. But we only went from 0 to 0.3 now, right? Because we did 3 steps of length 0.1. So instead of going from 0 all the way to 3, we went from 0 to 0.3. So how many would we need to do to get all the way out to 3? So we need about 30. So let's go down to, I don't know, about here. Say here, Control D, 2.8, 2 more will get us to 30. There, so now we've got down to y equals 3. So we want to actually extend this chart. So we'll just highlight those. So another thing you can do is if you pick this and then with this left click and then hold down the shift key. Click on that, scroll down, hold the shift key and click on that, and that selects that whole thing. So insert a table, recommended charts. And we would like the scatter plot that's got all the dots on it. Let's actually just get a nice smooth line. So that's a pretty good approximation. Of course, we got 2.89, and we know that the actual solution should be closer to 3.2 something. So we can actually, of course, make our delta t smaller by a factor of 10 again. But when we do that, we only got up to 0.3. So if we want to go from 0 to 3 in step size of 0.01, we're going to need 300 of these. And so it's going to involve a lot of scrolling. We'll pick one, we'll go down to 300, la la la. Click here, and then Control D. So we're actually only interested in getting to 3. So we'll clear those. So we got a much better approximation of 3.55. We're actually pretty close. And we can, of course, if I click on this and then scroll all the way up to the top and click on that, now I've shift click on that. Now I've highlighted that whole box, and we can go back to our insert. We can insert a chart. Let's do the line chart instead of the scatter chart. We have actually now have a pretty nice graph, reasonably accurate graph of what the solution curve looks like. And it looks more or less like that. And we're still a little bit short there because Euler's method can't quite make this turn around the minimum quite as fast as the solution to the differential equation does, but it does not too bad. And if we change delta t to 0.001, we'll get even better accuracy. So Euler's method works pretty well. You might have to crank the delta t down pretty small to actually get within, say, 2 decimals or 3 decimals or how many decimals you need. Excel can do that. You don't want to do that by hand. If you know how to program in Python, or if you know how to do other programming languages, you should be able to do this with a for loop. I'm assuming that my assumption for this course is that people don't know how to program generally. So I'm generally going to do stuff on Excel and on GeoGebra as much as I can. I'll use Maple sometimes too. So that gives us a nice picture of what a solution curve is, approximation to a solution curve. One other nice thing about Excel is I can change the initial condition. So we said, what does the solution curve look like that goes through 0, -3? Or we can also ask, what's the solution curve look like that goes through -2? And if I change that, everything else depends on that coordinate. So if I change that, everything changes, and we get a slightly different curve. If we make this equal to 0, so we're starting at 0, 0, right? We get a nice, there's an inflection point at 0, 0, and it just goes up. We've lost that minimum, right? If we go down to -5, we'll see the minimum again, right? And there's a minimum. And so if we go up to 1, right, there's no minimum at all. And note that when we get out to 3, right, our y values are jumping up pretty high, right? There's that exponential growth kicking in. Doesn't really look like exponential growth, right? But we're going from, 1 up to 14 pretty quickly there. So that's Euler's method, a little bit of way to play with that. You know, and you can change the initial condition as well. I mean, let's say we start at t is -2 and y equals -3. And there you can see that there's actually a maximum and a minimum, right? We've gone through the null line there a little bit. So we can get, even for solutions, even for equations that we can't solve, we can actually get decent pictures of what their solutions look like by using Euler's method, by using slope fields, and we can get approximations to what the solution curves are by using Euler's method. We will need to talk a little bit about error in Euler's method and error in numerical analysis generally, and also just sort of what should, how can we minimize that? One, let's see, how was I going to say this? So many of the differential equations we see are not equations that have a formal solution, formula that you can use. And so what you're going to need to do is be able to draw a slope field so you can visualize it. And you need to be able to do some kind of numerical analysis so that you can get numbers out of it. Okay, so that's this first lecture. And hopefully everything actually worked.